Hey everyone, welcome back to the channel. Giants of industry. A look at industrial fans. Industrial fans. We've all seen them. Towering figures in factories, warehouses, even large venues. They are the unsung heroes of air circulation, keeping us cool and comfortable. But have you ever stopped to think about the power they possess? These giants of industry are more than just spinning blades. They are marvels of engineering, designed to move vast volumes of air with precision. In this exploration, we journey into the heart of industrial fans. We unravel the secrets behind their remarkable ability to control our environment. Our focus? The often overlooked component, the fan blade. These meticulously crafted wings are the key to unlocking the fan's true potential. Join us as we delve into the fascinating world of fan mechanics. We'll uncover how subtle changes in blade design can dramatically impact airflow and energy consumption. Get ready to see these everyday machines in a whole new light. Our journey starts with a simple question: what makes a fan efficient? The answer lies in understanding the delicate balance between air delivery, speed, and reach. Each of these factors plays a crucial role in determining the fan's overall performance. The science of spin: understanding key fan parameters. Before we tinker with blades, we must grasp the language of fans. 3 key parameters dictate their performance: air delivery, speed, and reach. Think of air delivery as the fan's muscle. It's the sheer volume of air the fan can shift, measured in cubic feet per minute. A higher number means a stronger, more capable fan. Next, we have speed. This refers to how fast the fan blades rotate. Measured in revolutions per minute, speed directly influences the force with which air is propelled. A faster spin translates to a more powerful gust of wind. Finally, we have reach. This measures how far the fan's airflow extends. A fan with good reach can effectively cool a larger area, making it ideal for spacious environments. Now, where do fan blades fit into all of this? They are the sculptors of airflow, dictating how air is captured and propelled. The size, shape, and even the number of blades can dramatically influence each of these key parameters. Get ready. We're about to put theory into practice. In our next section, we'll roll up our sleeves and conduct an experiment. We'll explore how different blade configurations impact the performance of a typical industrial fan. Setting the stage. Our experiment with fan blades. To unravel the mysteries of fan blade design, we've designed a controlled experiment. Our goal is simple: to observe how different blade configurations impact a fan's performance. We'll be focusing on 3 key metrics: power consumption, airflow velocity, and noise levels. Our testing ground is a controlled environment, ensuring consistent conditions throughout the experiment. Our subject? A standard industrial fan, readily available and familiar in design. But our tools are anything but ordinary. We've enlisted the help of some sophisticated instruments to accurately measure our chosen metrics. First, we have the multimeter. This trusty tool will give us precise readings of the fan's power consumption in watts. Next in line is the anemometer. This device will capture the speed of the airflow generated by the fan, measured in feet per minute. Finally, we have the sound level meter. This instrument will quantify the noise produced by the fan, allowing us to assess its impact on the surrounding environment. With our instruments calibrated and our lab coats on, we're ready to begin. Our first test subject? The fan's default blade configuration. This will serve as our baseline, a point of reference against which we'll compare the performance of our modified designs. The baseline performance with default blades. Our experiment begins with the familiar hum of the industrial fan, equipped with its standard issue blades. This is our control, the benchmark against which we'll measure the impact of our blade modifications. We carefully record the data streaming from our instruments. The multimeter hums steadily, reporting a power consumption of 50 watts. The anemometer, positioned directly in the fan's airflow, displays an average velocity of 850 feet per minute. A gentle breeze, but nothing extraordinary. The sound level meter, meanwhile, registers a steady 70 decibels, a noticeable hum, but not uncomfortably loud. The default blades perform as expected, delivering a consistent flow of air with moderate energy consumption. The noise level, while present, is not disruptive. This baseline data is crucial. It provides the foundation against which we'll compare the performance of our modified blade configurations. Our next step will be replacing the default blades with a 3-blade configuration. Will this reduction in blade count translate to improved efficiency, or will it come at the cost of reduced airflow? Let's find out. Section 5, 3 blades take flight, efficiency versus output. With the default blades carefully removed, we install our first modified configuration, a sleek 3-blade design. The fan whirs back to life, its pitch subtly altered by the change in blade geometry. Our instruments, ever vigilant, spring into action, recording the impact of this modification. The multimeter, to our surprise, shows a slight decrease in power consumption. The 3-blade fan sips a mere 49 watts, a marginal but noticeable improvement over the default design. Have we stumbled upon a more energy-efficient configuration? Our attention shifts to the anemometer. Here, the impact of the 3-blade design is undeniable. The airflow velocity has dropped significantly, hovering around 700 feet per minute. It seems our quest for efficiency has come at a cost-reduced air movement. The sound level meter, however, paints a positive picture. The noise level remains relatively unchanged, indicating that the 3-blade design doesn't sacrifice acoustic comfort. Section 6-5 blades for maximum power airflow takes center stage. Our final act sees us pushing the boundaries of airflow with a 5-blade configuration. These additional blades, we hypothesize, will capture and move a greater volume of air. But will this come at the cost of increased energy consumption and noise? The multimeter confirms our suspicions. The 5-blade fan draws a considerable 56 watts of power, the highest energy consumption of all our tested configurations. Clearly, moving more air demands more energy. But the anemometer tells a compelling story. The 5-blade fan generates an impressive airflow velocity of 980 feet per minute. This is a significant improvement over both the default and 3-blade designs, confirming our hypothesis that more blades equal greater air movement. The trade-off? The sound level meter reveals a slight increase in noise, registering 73 decibels. The 5-blade fan, while powerful, is also noticeably louder. Section 7. Deciphering the data, comparing performance and efficiency. With our tests complete, we step back to analyze the data. Our experiment has revealed a fascinating interplay between blade design, airflow, and energy consumption. The default blades, as expected, offered a balanced performance, delivering adequate airflow with moderate energy consumption and noise. The 3-blade configuration proved to be the most energy efficient, consuming the least amount of power. However, this efficiency came at the cost of reduced airflow velocity. The 5-blade design, on the other hand, emerged as the airflow champion, generating the most powerful breeze. This performance, however, came at the expense of increased energy consumption and noise. Our findings highlight a fundamental truth. There is no one-size-fits-all solution when it comes to fan blade design. The optimal configuration depends entirely on the specific needs and priorities of the application. Section 8, Choosing Wisely, Finding the Perfect Fan for Your Needs. So, how do you choose the right fan for your specific needs? It all comes down to understanding the trade-offs and prioritizing your requirements. If energy efficiency is paramount, a fan with fewer blades might be the ideal choice. Be prepared, however, to accept a potentially lower airflow velocity. For applications demanding maximum air movement, a fan with more blades will deliver the goods. Keep in mind, though, that this power comes at the cost of increased energy consumption and noise. Don't overlook the importance of noise. In noise-sensitive environments, a fan with lower decibel output might be preferable, even if it means sacrificing some airflow power. The key is to strike a balance between performance, efficiency, and noise. By carefully considering these factors, you can select the perfect fan to keep your environment cool, comfortable, and productive. Section 9. The Power of Understanding, a Final Word. Our journey into the world of industrial fans has revealed the often hidden complexities of these everyday machines. We've seen firsthand how subtle changes in blade design can dramatically impact airflow, energy consumption, and noise, but perhaps more importantly, we've learned that there is no single best fan. The optimal choice depends entirely on the specific needs and priorities of the application. By understanding the science behind fan mechanics, we empower ourselves to make informed decisions that balance performance, efficiency, and comfort. So the next time you feel the gentle breeze of an industrial fan, take a moment to appreciate the engineering marvel spinning above. It's a testament to human ingenuity, a symphony of airflow orchestrated by the subtle dance of blades. And now, you understand the secrets behind its mesmerizing spin. Found this video helpful? Don't forget to give it a thumbs up, subscribe to the channel, and hit that notification bell. Thanks for watching.